The Zoom platform offers a number of means for interaction that we use. We would like to handle most questions at the end. To enter a question at any time during the lecture, click the Q&A icon and type in your question. You need not wait until the end. For those few persons joining by phone, we will unmute you at the end in case you have any questions. We might also unmute other questioners if they need to clarify their question. If you have a quick question for which you'd like an immediate answer, click the raise hand icon and enter the question. For these, the moderators will use their judgment about interrupting the presenter during the presentation. Also use raise hand to report any technical issue you might experience. There's also a chat option that allows you to type a message for all participants to see. Feel free to use that before the lecture starts to greet others. Be sure to use the all panelists and attendees option. I'll mention 3 other ways we use chat shortly. Like most of our GSM webinars, this one will be recorded. The full lecture schedule is on our website, gsmn.org. Thanks to Steve Erickson for arranging another outstanding slate of topics and presenters. As with our live lectures, this lecture is free and open to the public, not just GSM members. If you are not a GSM member, please open the chat box and type non-member and your city and state, province, or country. Also mention how you found out about us. We like to see how many non-members attend so we can see how well our information reaches the general public. So please do that for us. Thank you. Of course, we'd love for you to consider joining our organization. Membership information and forms are on our website. Membership dues are the primary method by which we fund these lectures and our other programs. Also, we can count the number of devices that tune in, but not the number of people watching from each. So we can get a better count of those participating. If you are watching with at least one other person, type 2 persons or whatever your number is in the chat box. Thank you. Continuing education credits. These lectures are eligible for 1 hour of CE credits. If that is something you can use chat to request a form. Include your name and email address. If you don't want everyone to see this information, there is a chat option that allows only the moderators to see what you type. Following the meeting, we will fill out a form, sign it, and email it to you. Are there any other announcements? Use raise hand if that's the case. Okay. Dr. Ben M. Frieman is currently a contract geologist with Ivanhoe Electric, conducting economic exploration. Previously, Ben was a postdoctoral fellow and research associate as part of the Laurentian University's Mineral Exploration Research Center, LU-MERC. There, Ben was part of a Metal Earth Research Initiative, which is focused on elucidating the lithotectonic evolution of the Archean Superior Province in order to better understand differential metal endowment in the region. This work utilized field-based investigators, isotope chemistry, geochemistry, and integrated geophysics. Prior to his time at LU-MERC, Ben completed his Ph.D. at the Colorado School of Mines in 2018. There, his dissertation work was similarly focused on the Superior Province and included both structural and multi-isotope detrital zircon investigations to constrain Archean geodynamic processes related to crust mantle evolution and how deformation processes influence the present-day distribution of base and precious metal deposits. Ben also attended the University of Maine, where he obtained a Master's of Science degree in Earth Sciences in 2012, and the University of Minnesota, where he obtained a Bachelor of Science degrees in Geology and Geophysics in 2010. Welcome, Ben.
Thank you so much for that fantastic introduction, Joe. I will, so you stop sharing, so now I can share, correct? Yep.
Yep.
Okay, we'll start sharing. We'll turn on the PowerPoint. Looks like, turn on my laser pointer. All right. So thank you so much again for that fantastic introduction. I was really excited when I got the invitation to give a talk to the Geological Society of Minnesota. So I am a native Minnesotan. I grew up in Inver Grove Heights. Obviously, I went to the U for my undergraduate degrees and still have a lot of family there. And I have a lot of love for Minnesota and its geology and people. And so I was really excited to be able to contribute here to your group. And today I'm really going to be focused on, as I said in the introduction, a billion years of early Earth's history. So, of course, northern Minnesota and into Canada in Ontario, there's some pretty old rocks, and I'll show you a lot about those today. And we'll get some perspectives on sort of the geodynamic history and the distribution of deposits, namely gold deposits in the region. So I did this work with Laurentian University. I was up there the last couple of years, sort of pre and during pandemic time, based out of Sudbury. But we were really focused on this Western Superior areas. So I was just super fortunate to work with this great group of kids, so-called Wabagoonies. I'll show you a bit more about them a bit later. A lot of great times doing research and looking at rocks and hanging out in the lakes of Northern Ontario. So this is a talk focused on mainly the Archean history of Ontario. And of course, you know, what's the problem with understanding Archean geodynamics? Well, first of all, the Archean, so this is, I like this time scale because it's kind of a circle here. So 0 would be at the very end of this circle, and the formation of the Earth here at sort of 12 noon. And as you can see, the Archean is actually about a third of Earth's history. And so it's a very long portion of Earth's history, something like 4.0 to about 2.5 billion years ago is the Archean. And we actually don't know, in modern times, we sort of know that there's subduction zones, there's a lot of magmatism associated with that. So you can think of places like South America, where there's a subduction zone and these big mountains and volcanoes associated with that. But we don't actually know when in Earth's history global plate tectonics actually started. So this is a hotly debated topic, both in academia and and whatnot. And you can see here on this diagram. So I've taken these first diagrams are going to be from Richard Palin and co-authors. He has some nice diagrams that show that there's a lot of different times that people have proposed that plate tectonics starts. So using a whole range of indicators, people have said it started as early as like just at the start of the Archean. Others have said that actually it was much earlier in Earth's history, something like 620 million years ago, and that's when we start to see things like high pressure rocks and blue schists and things in the rock record. So there's really no scientific consensus. This is sort of an ongoing argument. I also like to show this because I think it's easier to imagine what plate tectonics look like, since again, we can observe that today. But why don't we just start at the beginning? So at the very sort of earliest part of Earth's history, we would have had a magma ocean with a very thin protocrust sort of forming out of that. And this is the initial condition for most silicate bodies, sort of any planet that's a silicate-rich body would sort of start here. And then people think that we transitioned to a period that was dominated by what we call heat pipe volcanism. And this is basically where these residual partial melts just punch through that thin crust and you have really extensive volcanism at the Earth's surface. And this probably helped differentiate different parts of the Earth's mantle and give us more of a layered mantle like we see today. But then since the Earth was much hotter in the Archean, there's actually a lot of different varieties of behaviors we might expect. People think that it was dominated by sort of what you might call plume tectonics, or these squishy lid tectonics. So instead of being really rigid, the Earth's surface would have been really hot and actually deformed more ductily in a lot of cases. And then you have these sort of instabilities induced by these plume, and sort of drips off into the deep mantle. Also, you could build really thick piles of volcanic material here. And eventually, if you build them up enough, they'll become unstable and sort of drip off into the mantle, which would induce some upwelling and further volcanism. So these are sort of the dominant regimes that you might think of, sort of non-plate tectonic environments in the Archean. However, at some point, we do know we transitioned to plate tectonics. And so at some point, we probably transitioned to the subduction-dominated system, maybe somewhat similar to modern environments where you have mid-ocean ridges where new crust is formed, and then interaction between ocean and continental crust and subduction. At some point, there's dehydration reactions and melting induced in the mantle, and then all this volcanism and island arc activity. Like I said, just like you might see in South America today. Could also be a little bit different since everything was much hotter. It could be basically a shallow slab subduction. So instead of being steeper here, you might have a very small bit of mantle wedge, and that produces sort of a different pattern of geochemistry than you might see in this type of environment. I also alluded to this on the previous slide, but sort of one of the major arguments is that actually if you build up this really thick pile and bury crust thick enough, you can actually get dehydration reactions at the base of this giant volcanic pile, which could induce melting and give you sort of similar types of magnetism that you might see in some of these subduction-like environments. And this could also be influenced by mantle plumes and things. So mostly we think at the time periods I'm going to be talking about, you're probably either plume-dominated or the subduction-dominated system. So this diagram I know is a little complex, but it's basically just, I like to show it, it's the area of emerged continents versus time. So Earth's formation sort of back here. So like I was just saying in the earlier slides, we don't think there was much tectonics in at least the earliest parts of Earth's history. These heat pipe and squishy lid sort of worlds probably dominated after that. However, it's very likely that we had maybe some isolated or some sort of nascent stages of subduction happening after that. And then some people have theorized that then we transition to this mobile lid tectonics, something closer to modern day subduction, until we get closer to this modern day style where it's much colder, steep subduction processes. So really, this is an extremely important time of transition in Earth's history, sort of this 3.6 to 2.7 billion year range, where we transition from these sort of early geodynamic processes to these more modern styles of geodynamic environments. So this 3.6 to 2.7 is a critical part in Earth's history. So not only that, but there's a ton of economic deposits hosted in Archean domains, not just in Canada, but across the world, Australia and whatnot. So how did these variations in geodynamic environment affect the distribution and style of these economic deposit formation? So lucky for us, we're in North America, and it's one of the best places to study these things. Because all this stuff in red here is basically Archean rocks, more or less. Most of you are probably in the Twin Cities or nearby in Minnesota. So, most of Minnesota is underlain by these Archean rocks, and of course, all of northern Minnesota and into Ontario, where we're going to focus today. And it's mostly dominated by the core of North America, which is this called the Superior Province, or the Canadian Shield, you might hear thrown about. So we're really just going to focus on the Superior today. So this is a map I put together for some of my recent publications, and this is showing the Superior Province. colored sort of by age history. So things in blue are sort of younger. There's juvenile Archean rocks, so they're Neoarchean in age, about 2.7 billion years old. The stuff in purple are domains that are dominated by older rocks, Mesoarchean, which is 2,800 million years ago to 3,200. And then there are other domains that have a bit older history into the Paleoarchean up to 3.6 billion years ago. And actually, I'll show you a lot of data from here that suggests maybe I need to add some more blue to this map, because there's actually some pretty old rocks I've been able to study there. So the present day configuration of the Superior Province largely reflects when all these different domains were sort of crunched together at the end of the Neoarchean at about 2.72 to 2.65 billion years ago. There's some correlative rocks. I'll show you a bit, poke out the Morton gneiss and things that poke out in the Minnesota River Valley. There's a lot of building stone of the Morton gneiss. This beautiful megmatitic gneiss also has a really old correlative history to some of what I'm going to talk about today, deep into the Paleoarchean. Okay, and I mentioned this a couple of times, the economic significance, I don't think we can overlook. So especially for Canada, it's a major Canadian industry. So this is showing on the left, this is the value of mineral production, actually in Canadian dollars, from preliminary estimates, and then actual numbers in 2018 and 2019, sort of pre-pandemic. And what this shows is that mining is a huge industry in Canada. It's a large portion of their GDP. This $50 billion roughly actually every year in terms of actual mineral production out of the ground. You can see that Ontario and Quebec, which are dominated by the Superior Province, account for roughly, the Superior is about over 35% of the total production of mineral production in Canada annually. And it's not only production, but it's also exploration. So these preliminary numbers from 2019 are broken down by the different types of mineral resources that are being explored for. And you can see this is dominated by precious metals. This is basically gold and silver. Base metals, this would be kind of like lead, zinc mostly. And then some of the others are less dominant. But if you break this down, that's basically 1.2 billion more dollars spent on just looking for more deposits to mine annually in Canada. So it's hugely important to the Canadian economy. So what do I mean by different ore forming processes? So in the Superior Province, basically all the, excuse me, the base metal deposits, some of which are pretty gold rich, largely formed at the seafloor at the time that those domains of the Superior Province were forming. So there's a pretty correlative to like black smokers that you might see in the modern seafloor. And basically they're massive sulfide deposits that form at these sort of subsea floor vents. And you can see a cross section of what one of those might look like with sort of feeder faults and things, and building a sulfide deposit here. So these relate to volcanic construction. So whenever those individual domains actually formed. And then the major gold deposits are actually these orogenic gold deposits. So these you can see, so like the Mother Lode deposit in California is a good, more modern example of these. And basically we think these form along these giant crustal scale fault zones. So not exactly when the domains were forming, but when they're sort of crunching together, either by plate or non-plate tectonic processes, you release a bunch of fluids when you crunch everything together and localize them up these big fault zones. And then you can concentrate the gold in these big fault controlled systems. And these tend to be related to a little bit younger events, like I said, these regional deformation histories. Again, these sort of vein-hosted gold deposits. So these are sort of the two major deposit types that we're really going to focus on today, mostly the orogenic gold. The other part of it is that, you know, not every domain has the same amount of gold. So this is gold grade. So really high grades would be higher up on this y-axis. And this is total tonnage. So you might have really high grades, but unless you have a lot of it, it doesn't really, it's not really that conducive to make a mine. And so what I'm showing here in red squares are data from the Dryden area where we're going to focus in today, the Timmins area, which is a world-class camp further east in Ontario, and then a correlative area about the same age as these in Australia, this Kalgoorlie area. And what you can see is Timmins and Kalgoorlie have a lot of decently high grade, but really large tonnage deposits. That's why these districts have a lot of mines. They have these really big deposits. It's not to say that the Dryden area doesn't have any deposits. They just tend to either be high grade and small, or don't quite make the cut to make really world-class deposits. So there's a lot of open questions in our research realm, whether this relates to a lack of exploration, is there fundamental differences in the deformation history in these areas, or is it that they have completely different lithospheric evolution in architecture that is controlling the endowment of these regions? Or is it simply that, well, you know, one's in a subduction setting, one's not, or it's a slightly different variety of flavor of geodynamic environments? So these are sort of open questions which Metal Earth at Laurentian was sort of looking to address. So Metal Earth is this big federally funded project. It's primarily funded by the Canada First Research Excellence Fund, which is a federal program looking to generate new science to address a wide range of things, not just geology. And so the idea was that this Abitibi area, which has a lot, so Timmins is sitting right over here where there's a lot of world-class camps. So Abitibi is sort of famous for having a lot of giant deposits, where in the Wabigoon area, there's not as many as I alluded to on that previous slide. And so they decided to do a bunch of seismic studies. So each one of these transect areas, the Abitibi ones, Chibougamau, Malartic, Rouyn-Noranda, Kirkland Lake, Matheson, Swayze, each one of these areas has had a postdoc like me who was focused on doing a lot of new research to sort of understand the geology and history of these regions. And the idea was to directly compare those with the same weighting to the western, to the Wabigoon study areas in the eastern Wabigoon, Sturgeon Lake, where I was working in Dryden, and then at Rainy River, all the way down to the Minnesota border here at I Falls. So equal study, equal amount of money put into both of these areas to try and find out factors that we might be able to figure out why exactly that there's more deposits in one versus the other. All right, so they're quite similar, although they have different amounts of gold. The southern Abitibi sort of, and maybe every greenstone belt, so Archean domain in the world, has a similar history. So the Abitibi, because it has so much gold, is super well studied. We know the age of things, but basically all the older rocks are these volcanic piles and things. So at the time when these VMS deposits could form, basically you have all this subsea floor volcanism. At some point that volcanism gets cut off. In the Abitibi, it's about 2690 million years ago. And then you see everything shift. That's the time when deformation starts, everything's starting to get crunched together, and you see these sedimentary rocks overlying these volcanic rocks at the time when this deformation happens. In the Abitibi, we can recognize several different types of sedimentary packages, some deep water successions, and then there's even unconformities between the two. So there's further deformation and then different types of deposits, sedimentary deposits on top of it. These so-called Temiskaming deposits are quite famous for being these shallow marine to subaerial alluvial fluvial, so river systems at that time. And although the Wabigoon, we sort of generally know the same type of things happen. Everything's just a tad bit older. There's these volcanic rocks, there's these same deep marine sediments, and then these alluvial fluvial successions. So the same general progression holds true at where there's this volcanic construction transitioning to, deformation and deposit of these sedimentary sequences. But there's also these older rocks, these gneissic plutonic domains, and the contact relationship between all these and their relative ages was much less understood in the Western Wabigoon versus the Abitibi. So a lot of my research, since I did my PhD on the Abitibi, was sort of look at the same, do the same types of things in the Western Wabigoon and see what I could figure out. So again, while the rocks are similar, the broad Archean histories, may be a bit different. So it says differences in inherited crustal architecture, these older rocks of gneissic plutonic rocks. Hold on, I gotta move this dang Zoom window. Okay. So like I said, the goal of Metal Earth is to figure out why these different provinces have a different endowment. And the way we decided to do this was a whole bunch of new field work. So boots on the ground geology, mapping and things, geochronology. So I'll show you a lot of Zircon data that I did there, geochemical indicators and things. And then they also ran a wide range of geophysical data sets, namely magnetotellurics and seismic surveys, to get a deeper perspective at what's in the crust. So the Abitibi has many world-class deposits. Known gold deposits are more than 300 million ounces of gold, and then more than 800 million tons of this polymetallic ore in these VMS type systems, these base metal systems. Whereas the Wabigoon, the only world-class deposit known in that area is the Rainy River deposit, which they started mining in the last few years. And total known gold endowment is only about 15 million ounces. So this is an order of magnitude, much less economic deposits in the Western Wabigoon versus the Abitibi. I don't want to oversell myself in the work that I've done there. It's not just important for Canadian economy, but I was also looking to build expertise in Canada. So that's another big part of it. So there was 5 new faculty hired as part of this project. I was one of 30 some odd postdoctoral associates, a bunch of technical support staff, lab technicians, a whole cadre of PhD, master's students, and bachelor students. And this is just a portion of them. This isn't even all of them sitting here happily in front of our building in Sudbury in 2019, pre-pandemic. And then this is mentored by some of these guys who've worked in the Archean for quite a while: Harold Gibson, Bruno LaFrance, and John Ayer, as well as Phil Thurston. So it's a big collaborative research project. I just wanted to emphasize that wasn't just me. And yeah, there I am. If you can't find Ben in the crowd, there I am. So I was also super lucky. So I headed up, basically, I wasn't only doing my own research, but I was sort of a field supervisors for a big group of graduate students. So me and Dr. Stefan Peruti here, we're sort of supervising all these students in the field. Steph has a PhD student, Becky, who started publishing some of her research. She's looking at sort of using GIS techniques to sort of understand where and why some deposits are where they are. So prospectivity analysis is called. We also had David, who was looking at intrusion-related deposits. Mokalani, who was doing some work looking at the big plutons up in the Dryden area, where they actually want to put nuclear waste repository up there. There's ongoing studies for that. Kendra, who looked at the structural history. And then we had a whole series of really great undergraduate students who did honors theses with us and also worked as our field assistants. Not all of them are pictured here, but this is Lauren, Jordan, and Kat, many of whom have gone on to pretty awesome careers so far. These guys are up in Newfoundland working for companies, and Kat's at UBC Okanagan working on her master's degree now. So I'm not going to dive into their research today, but they were fantastic and contributed lots of very interesting things. I'd encourage you to look up their theses or send me an email. I can send you some information. Okay, so my main focus for for the research was in the southwestern Superior Province. So if we zoom in here, just north of Minnesota, so there's Thunder Bay, I Falls is about there. So I've been mainly focused in the Dryden region. And in this area, basically there's four major geologic domains. There's this eastern Wabigoon subprovince, this western Wabigoon subprovince where you see a lot of these greens. That's where a lot of those volcanic rocks are. Whereas all the pinks and stuff are mostly dominate these two other regions, what's called the Winnipeg River subprovince, and then the Marmion subprovince. And so in 2 slides, I'm going to show you a map for this area where I spent most of my time doing the research. But I just wanted to show you this picture. So that whole sort of perspective on the distribution of those different terrains or domains was sort of well known prior to us going up there to work. So these are neodymium isotopes, which basically give us some perspective on sort of the inheritance that's in the rocks. And what you can see in the Western Wabigoon, you're dominated by these blue colors, which are more juvenile, so like younger inheritance or little inheritance, similar to the Eastern Wabigoon. But you can see these Winnipeg River and Marmion domains have these warmer colors, which relate to having an older prehistory relative to these juvenile domains. So something into the Mesoarchean, 3 billion years and older. So a lot of these lines were sort of drawn based on this perspective, but you can see that there's not a ton of data in a lot of these areas here, especially, and they're limited to certain parts of the belt. And again, it's not that there's no economic deposits. There's just tend to be much smaller. So I've just highlighted 5 or so here. I guess these ones aren't labeled at Ken West, but basically they tend to be 1 or 2 million ounces. There's some good deposits in Cameron Lake. Oh, the numbers got buggered. That's what it was. Sorry about that. And there is a pretty big deposit that's hosted in the Marmion, this Hammond Reef deposit, which is about 5 million ounces. So that's a really big gold deposit. It's not that there's no gold deposits. There's just not hundreds of million ounces of known gold. So just to give you a sense of the numbers, like I said, we thought going in that the Winnipeg River, we knew it had some older ages to it, whereas the Western Wabigoon, this stuff in the middle here in the green, is only Neoarchean at 2750, 2720 mostly in these juvenile rocks. This Marmion, we knew it's a bit older, that's Meso to Neoarchean in age. And these two are the Winnipeg River and the Marmion, you can see they're dominated by these sort of pinks and reds colors because those are gneissic plutonic rocks as opposed to volcanic rocks. And I showed this earlier just to remind you that the pinks, again, are some of these light pinks are these gneisses where it's the same stratigraphic evolution, very similar to the Abitibi. So I'm going to show you 2 studies today. And I'll try and be quick about it. There's some technical data in there that I'll explain in some detail, but I'll glaze over some of the really technical aspects. So the first study was focused on this area of the Winnipeg River, where there's these beautiful gneissic plutonic rocks exposed. And then the second one is where we have the contact between the Winnipeg River and Marmion subprovinces. So in this beautiful alluvial-fluvial succession, so this youngest rocks in contact with some of these older rocks to really trying to get at this relationship of these Neoarchean stuff to these older rocks. So I'll touch on the geodynamic setting, lithotectonic evolution, and look at these older rocks as well as the younger things. And then we're going to talk about the broader architecture and how that might have influenced the evolution and metallogenesis, so the formation of deposits. And I'll show you a bunch of regional to outcrop scale mapping, some Zircon data from laser ablation data, a bit of geophysical surveys, and then I'll try and integrate that all together for you. And again, this is a beautiful country to do field work because you can cruise around on a canoe. We have a little 3-horse motor on this flat back canoe, and we cruise around on the lakes doing a lot of mapping. So a lot of fantastic work done up in Ontario. So I'm going to show you a whole whack of Zircon data, which I just wanted to touch on sort of what that entails. So exactly how we collect this data. So basically we get a rock sample from the field. So we go out to an outcrop and bang it off and fill a bucket. We smash up that bucket and separate out individual grains of sand essentially out of it. And then we pick out these grains of zircon, and zircon's great because it locks in several different types of isotopes that we can use for analyses. So we image them up, we look at the sort of internal sort of heterogeneity in those zircons. So this is 100 microns, so kind of like the width of a hair or a grain of sand. And then we laser it. So we use a laser to blast the zircon in situ. Oh, I have to do that. So I'm just going to start this animation. So basically you shoot a laser. These are little laser pit holes here. And you suck it up into a mass spectrometer. So this is just a little cartoon of that. So we suck it up into a mass spectrometer, run it through magnets and things so we can separate out the different masses of elements in that zircon. And then you can count up how many times those different elements hit these detection plates. And then you can figure out how much different types of isotopes are in there. So uranium and lead system is good for actually dating the rock. So figuring out when the zircon crystallized. This is just a plot, a Concordia diagram that we use to evaluate the data. So basically you get the age of the individual zircon grains. And then we can also look at the hafnium isotopes. And so the hafnium isotopes we plot up in this epsilon range. So we combine that with the ages of the zircon. And then you can figure out exactly when, what type of signature that the magma from which that crystallized records. So if we have some really juvenile rocks, something like at a mid-ocean ridge, maybe it would tend to be more positive. If it's crustal derived, it tends to be more negative. And if it's primitive, that might be sort of a really deep mantle source, something like a plume source, like you might see in Iceland or Hawaii. So I just wanted to highlight this because I'm going to show you a bunch of data from it. So prior to working in the Winnipeg River, we sort of knew there were old rocks. So this is actual previous data from the Winnipeg River. So this is that epsilon hafnium value. And you can see everything in this age range is very positive, but everything in this age range is very negative. And you can actually project back and think about what sort of crust it was derived from. So where these inclined lines hit either this primitive mantle or depleted mantle, that means actually it's felsic crust that was derived from even older material, maybe as old as 3,500, but we can never find these rocks actually. So this sort of tells us that there was old rocks kicking around, but we had no idea where they were. So I did a bunch of mapping right here. So this area is on the road to Red Lake. It's actually pretty easy to get to. And it's this beautiful area of gneisses. So this is the road to Red Lake from Kenora, and I cruised around. So some of those samples I just showed you were actually collected from right here on Cedar Lake. So they're pretty old, 3.25. There's some younger stuff. They're sort of swimming. These are gneisses swimming in a sea of younger rocks, these tonalites that are about 2,700. And we're going to zoom in on this sample real quick. So this data from this study is only on this one rock from this one sample that actually looks like this. So it's this really banded gneiss. That's pretty complex deformation history, but looking at it, you might not think it's that special. But what makes it pretty special is that if we look at the zircon grains, so this is cathode luminescence, so this is zircon textures that you can see different growth zones in the zircon, and the circles are where I lasered them, and you can see these really old cores, about 3550 MA in a lot of these grains, and some younger stuff, these 3350 grains. So this is the oldest set of grains, and this was really surprising because, as I showed you in the previous slides, we had never been able to find these really old rocks in the Winnipeg River. And this actually makes this, excuse me, the oldest rock known in the entire Southern Superior Province of Canada. So it's one of these old rocks that has a really long and rough life. So it's really hard to preserve these types of rocks. And it was really surprising when we first got the data back. Not only that, we can look at different trace elements, sort of the details of this don't really matter for the point of this talk, but we can look at different trace elements also in addition, in addition to those different isotopic systems, and it sort of infer the history of the zircons that they're recording. So it looks like the older stuff is related to this primary magmatic signature, whereas those younger overgrowths relate to further deformation and remelting of that rock. And what's really cool is all the older rocks plot really close to this ocean island basalt domain. So this is things like Iceland or primitive mantle material, basically where we're deriving really deep mantle sources to for our melts. So it looks like it's a felsic melt from something that was derived in ocean island basalt, sort of like Hawaii or Iceland today. And then there's even further differentiation as recorded by these younger grains in these uranium, ytterbium, niobium, ytterbium diagrams. So again, this is not only telling us the age that these rocks form, but also a bit about the geodynamic setting and environment that this particular rock records. I don't want to get into too much detail about the hafnium isotope, but this is a really cool data set. So I just wanted to show it. So again, those the oldest zircon ages we have are here, but like I showed you on those earlier diagrams, we can sort of speculate on what if it was derived by melting of older material. It actually suggests that it was derived from melting of something that was about 3600 MA, so even older yet, but not preserved in the zircon record. So we're actually taking some older crust, melting it to make this rock, and then we have a bunch of younger events that are working and reworking this guy. And this is just to show you that that it's not a lead loss story. So I said, wow, this is crazy. We got the oldest rock in Southern Superior of Canada. And how does this compare to the rest of the world? Basically, this is a compilation of data from in South Africa, really old craton, stuff in the Minnesota River Valley, as well as parts of Australia and India where there's known rocks. And the long and short of it is, it looks like they all have a pretty similar history, suggesting that they might have a sort of a shared history, or maybe even formed as sort of a proto-continent during this starting in this Paleoarchean time period, but then moving into the Meso and Neoarchean. So we don't really know. It's hard to it's hard to know if all these rocks form the same continent or if they're just little individual domains at this time. But at the very least, we can sort of say that this was a really major period early in Earth's history where we have crustal growth and actually formation of continental crust. So it's a pretty cool story coming out of just one rock from zircon grains in geochemistry. So, you know, what did this look like? Basically, I'm saying that there's sort of this, felsic crust that formed in this sort of plume-induced setting. All the younger sort of grains might relate to when different of these initial sort of older continental crusts started interacting and forming sort of nascent subduction zones and things. Then they amalgamate together, and so it's sort of the beginning of plate tectonic-like systems in sort of plume-induced environments. So while it's maybe not exactly like we see today, it tells us quite a bit about sort of the onset of this transitional period there, where we get the first sort of really larger stabilized continents and transition to these subduction-like settings. So this is sort of what I'm arguing, what's recorded in those rocks with comparison to a global record. Okay. So that's from the Wabagoon study. So I'm going to go through these last studies pretty quick, but I want to show you some of this data because it's pretty cool. So again, we're going to zoom down to the south here, where there's these youngest rocks in the belt, this stormy basin, and then where it's in, where some of these the Wabagoon is in contact with gneissic rocks of this Marmion subprovince. And so if we zoom in on that basin, it's again these younger age about Neoarchean, and then there's this big hunk in fault zone, which is very similar to other fault zones in the Abitibi where there's lots of gold. There's little gold occurrences here, but there's no real big deposits or anything. And I just want to zoom in on this area because I did a bunch of mapping there. I ran some field trips, and you can look at some of the field guides that are with the Ontario Survey. And basically there's this perfect road here that cuts right through a couple kilometers of this basin. It's where they've done a lot of logging, so the rocks are pretty well exposed. It allows us to define the temporal and geochemical variations in the basin. So I just want to show you this one map here. So I did a lot of mapping. I was able to outline the different layers in the rock. And you look at these things and they're pretty fantastic. So this is sitting right there along this little logging road. And you can see these crazy volcanic deposits that look like they were almost deposited yesterday. These are basically graded tuffs and pilly ash tuffs. So this is telling us that the sedimentary basin also has a lot of sort of volcanic and volcanic clastic activity associated with it. These other tuff breccia units are sort of these big pyroclastic flow deposits that are interbedded with sandstones and things that are related to more of like the river system environment. So this sort of tells us the environment at 2700 looks like we have a really active volcanic environment. These rocks are in contact with this intrusive rock here, which is this thundercloud porphyry. We didn't really know the age of it, so we did some high resolution geochronology with this TIMS method combined with this laser method. So we were able to show, okay, this intrusion is actually the same age as this basin. But when we lasered the grains, not only did we get the age at which the granite was emplaced, but we get all these older ages, some as old as 3 GA, 2.8 GA. A whole bunch of inheritance is also recorded in this granite. So I wanted to compare that to the Marmion subprovince. So I did a bunch of mapping here, did a bunch of structural mapping. I collected a whole bunch more samples for geochronology. So this is just a summary of those textures. And then these grains aren't quite as old as what I was seeing in the Winnipeg River, but you can see pretty crazy textures, cores in this 2800 to 2900 age, and these more broad domains and with a bunch of Neoarchean overgrowths. So basically this Marmion domain not only has this older Mesoarchean history, but it also looks like it was pretty heavily reworked at the time that the Wabagoon was forming. And then I just want to highlight this one sample. I'm going to show you something from that. And this is the same age as that stormy basin, and I'll show you some of the geochemistry. So if we compare the zircon from the inheritance there to what I got in the Marmion, you can see sort of a barcode between these two domains. It looks really similar. So it looks like this intrusive rock is actually picking up a lot of this Marmion material here, and it has the same signature. And we did a little bit, we have some seismic here. And so I interpreted this, basically, this is where that granite would be, and there's that stormy basin. And this thing, the Marmion domain projects underneath it here. And so I was able to sort of establish that in the southern part of the domain, we're actually building this Neoarchean basin and volcanic system right on top of this Marmion crust. And what's really cool is if I show you a bit of regional data from stuff that's a little bit older than this basin, so as well as younger, the Islet Stock, Ravel batholith, and this Atiquo Lawrence batholith, so more central to the Wabagoon, we actually see a really interesting pattern. Stuff in the Atiquo Lawrence on the other side of this fault zone actually has a more depleted mantle source, so something more like mid-ocean ridge basalts, whereas everything over here, the Islet Stock and the Ravel batholith, regardless of age, have this crustal signature more similar to an evolved continental crust. And this is one last thing. So you can also analyze in the Zircon a bit of other redox sensitive trace elements. And basically things that are more positive here really are more hydrous. So there's actually water in the melts. So everything that's older tends to cluster around 0. So they're not quite as oxidized, where we see this big jump in the Neoarchean time where things are much more wet. So what this suggests is that all these magmas have a lot more water in them. So not only are we building volcanics on an older continental margin, it looks like it might be an actual continental arc. So we have subduction there. We're getting hydrous melts produced. So it's actually much wetter tectonic setting. So what's the broader implications of all this? I'll sort of wrap up everything here. I know it's sort of a whirlwind of data and stuff. I'm happy to answer more questions, but I wanted to at least sort of give you the broad brush strokes from some of my detailed research I did up there. So the implications are, if we're building this Western Wabigoon right on the margin of this continental crust of the Marmion, so we saw from the Marmion data that there's really long history. There's like a couple 100 million years of working and reworking. And what that means is when you sort of work and rework these type of crusts, we're actually going to really dry it out and make it pretty infertile. So although we have hydrous melts, perhaps coming from the mantle, we're actually sort of already soaked this sponge dry after hundreds of millions of years of working and reworking. So we're not going to actually get a lot of gold out of this crust unless we have a way to get it directly from the mantle to higher levels in the crust. And we think that happens on the other side of this regional deformation zone. So I didn't get into it in this talk, but these big black zones here are big regional fault zones. And we think these mark sort of breaks in big crustal scale architecture, whereas on this side of the fault zone, there's more limited gold availability. And on the other side, we actually have more truly juvenile rocks and have a much stronger connection from mantle to crust, which allows us to get more gold there. Whereas over here, we have this sort of underlying dry and infertile crust of this multiply reworked domains. So we think that this Marmion deformation zone is what this particular guy is called, marks a long-lived sort of lithospheric scale structure, probably relating to even older shared history between the Winnipeg River and Marmion. So it's basically telling us something about the architecture of the whole belt and why the gold is where it is. So again, it's more juvenile over here. That's why all our deposits are clustered here, and much more limited, although cool in a continental arc, that doesn't have a lot of gold in this case. And so we might want to focus, if you're doing exploration, on these big northeast trending structures, this Manitou to Norwich deformation zone, this Marmion deformation zone, which also happens to host the other big deposit, where we actually have these big crustal scale structures, allowing us to suck the gold out of the mantle and get it up into the crust. All right, so just to synthesize all that, again, I hope you learned a bit today. This area of the Southwest Superior Province, not only beautiful for so many reasons, records nearly 1 billion years of Earth's history in the Archean. So the earliest origins are in the Eoarchean at about 36 to 3500 MA and Paleoarchean. The area records further stabilization of continental crust as recorded in the Marmion and Winnipeg River some provinces. And then it has this fantastic Neoarchean history, which we think is a really good example of a continental arc to back arc setting, which are pretty rare to find actually with good evidence in the Archean. And as I showed you today, I think the distribution of prospective domains is largely controlled by a bit of these earlier geodynamic processes, which set up this crustal scale heterogeneity and really sort of set up where different parts of these domains were able to sort of connect better with the mantle and get some gold deposits. So that's all I'm going to talk about today. Again, I hope you have questions. If you don't want to ask it here today, feel free to email me at either of these email addresses work good. I'm pretty active on ResearchGate, so a lot of the papers we've been publishing are freely available on there, or send me an email. And again, big thanks to Metal Earth and the Canada First Research Excellence Fund, which funded a lot of this research. And with that, I'll take any questions.
Well, Ben, thank you for a fascinating and rather complex talk about areas in Canada that I think has, at least in my mind, raised questions about parallels on our side of the border. Let's take a look and see what we've got in terms of questions here.
So I see one.
One is, pardon?
Oh, no, go ahead. I was just going to say, I see one from Pete. He says, are you experiencing in Canada the same opposition to mining metal in nice canoeing areas that we are having here in Minnesota? So that's a great question, Pete. Yes and no. So particularly in this area I mean, I've shown, 10 beautiful pictures of lakes here. There's actually plans to put in some mines. And as I said, there's a plan to actually put in a nuclear waste repository up in this particular region. So it's a bit of a mixed bag. So Canada in general has very robust framework for doing mining safely, I guess is what I would say. So there's a very good regulation in Canada, wherein and in the US as well. But when anytime you build a mine, you have to put up all the money from construction through remediation and monitoring. So there's it's still mixed. Obviously, you want to do mining safely, and you don't want to ruin pristine natural habitats and things. But in general, it's easier to make mining happen in Canada because they have pretty good regulation for it. And again, it tends to be a big part of their economy. One other thing, especially in these regions, it's pretty sparsely populated. There's not too many people. There's a lot of tourism industry. It's certainly important, but this area of Kenora and Ontario, right? It's mostly us Americans going up there that sort of fuel the whole economy for the region. So there's a lot of considerations going into like making sure they don't mess up that economy through mining and things. But it depends on what type of your deposit you're looking at and what type of environmental concerns. I would say it can certainly be done safely, but with due diligence. So I hope that makes sense.
Okay, and let's see, we have another question here. What type of seismic did you use? What depths and densities did you look at?
Yeah, thanks, Mike. So this was a vibrasize survey. So it's actually a truck that vibrates to create the seismic source to use to make the imagery. It was mostly post-processed by third parties and things. So the densities in these hard rock domains, seismic can be super hard to do. Some of the vibrasize, we do have some surveys that go down 30, 40 kilometers and sort of let us look at this broader architecture. That section I showed you is a shorter survey that doesn't have as deep of depths. And basically it's about, 10 to 15 kilometers depth that you can see really, really nicely. So it's vibrasize and crustal scale depths. There's a bunch of old surveys in the area from what's called lithoprobe. So in the 90s and 2000s, there was another big seismic survey, and that was designed, that went all across Canada, and some of those lines go through there. And that was designed to look much deeper at moho depths, so sort of the base of the lithosphere. And so we can combine those data sets a little bit with some of these other perspectives to get a full sort of crust lithosphere perspective.
Okay,
Yeah.
for Randy Strobel, are the greenstone belts the green areas on your maps?
Yes. Yep. So the greenstone areas, on this particular map, these are all basically basalts and andesites. So all this greens and yellows are these what we would call greenstone, and those tend to be dominated by basaltic rocks. So pillow basalts and things like that that were emplaced at the seafloor. So all these greens are, yes, the greenstone belts in this case.
Let's see, any other questions?
There's another one in chat, Joe.
Let's see.
From Mary Ellen.
Mary asks, you were referring to gold versus base metals, but how much platinum is being found in these two regions, and does that differ as well? And how much rare earths? Only uranium was mentioned of those. Yeah, that's a great question, Mary. I didn't get into that too much. Platinum mostly comes out of like layered mafic intrusive deposits. So there are, the stuff that's in northern Minnesota. It's not quite on this map. is where you get some of the platinum. So the platinum PGE stuff that they're talking about mining in Minnesota it's a little less common deposit type. So although it is a bit variable between the regions, it's not quite as variable because it just tends to be a more rare deposit type. Basically, you have mafic intrusion coming in usually, and you get sort of layering in that when it's sort of crystallizing. So those exist in both areas. They're just not super common in either. They're kind of these PGE deposits occur in both. But there are more in the East, but I don't have the numbers on that. I didn't mention much about rare earths, but these gneissic domains, they have a lot of pegmatites in them, and especially here and in Manitoba, these domains are actually pretty, people are exploring them for rare earth elements and in pegmatite deposits. So it's a major sort of component to the exploration in these regions, but gold and base metals really dominate the market. So I focused on those here. Hopefully, does that answer your question? I hope.
Let's see, Mary Helen's got a raised hand.
I'm fine with letting her talk if she would like. It's okay. Some audience interaction is always good.
No, I think she's letting us know how many people are at her location.
Ah, okay,
No.
good.
Let's see, Dave, you pick up any other questions?
I don't see anything else in chat, and I don't see anything else in Q&A either. I didn't see anything at all in Q&A.
Okay. Well, Ben, thank you very much for a fascinating discussion. We're glad you could make it. And those of you listening, we hope to see you again 2 weeks from tonight. Take care and have a happy Thanksgiving.